tidal hybrid rocky wall system with locally heat-treated replaceable bars for hysteretic energy dissipation, which is done by myself, Dimitrios Kalyonzis, Marshall Morrison, Andy Yu, and Mariam Nazari. So many of you may be familiar with the hybrid rocky wall system, which is a rocky wall system that achieves resendering through unbodied post-tensioning and also uses energy dissipation bars to enhance its hysteretic damping capability. However, in the classical hybrid rocking wall system that is shown in part A of this figure, these bars are mostly placed near the wall center, and because of that, the bars cannot be easily replaced unless there is a significant intervention within the wall centroid. So we worked on a different concept where the hybrid rocking wall uses locally heat-treated bars. So in this case, the bars are similarly disembodied over a region, and then, but instead of placing them near the wall centroid, we place them near the wall ends. And one modification that we are introducing here, instead of having a uniform bar, we locally heat treated one section of the bar, and the reason for that is to concentrate all the hysteretic energy dissipation within this section. So as you see from the force versus displacement curve of this bar, the local heat treatment, what it does is that it reduces the strength of the bar below the original yield strength, and also increases its elongation. By doing so, we ensure by equilibrium of axial force along the bar axis that the energy dissipation and damage will be concentrated within a specific region that is located in a ground pocket. By doing so, we know from beforehand where the energy dissipation is going to be concentrated, and therefore we have a replaceable bar section that is more easily accessible, as the bar will be near the end of the wall where we have better access, and we don't have to intervene within a region that is close to the unbodied post-tensioning and will probably require significant cut of the transverse reinforcement as well. So the question now is, why should we use heat treatment? Because in the past there have been other methods of localizing the energy dissipation in bars, such as machining and to create a dog bone bar section, or using bars with smaller diameter between segments that would be established through the use of mechanical couplers. So first of all, heat treatment has a much lower cost that, based on our experiences, is going to be about or less than $5 per bar, while machining the cost of bars would probably end up being $50 to $100 per bar, and specifically ending couplers could also increase the cost further. Moreover, heat treating industry can easily provide these services of heat treatment, and the civil construction companies do not necessarily need to become experts in heat treatment. So essentially, they can just send the bars to a heat treating industry company, and then they will do the heat treatment for you. Another benefit of using this approach is that the heat treatment is going to preserve the geometry of the bar and can be performed offsite, which reduces the impact to the wall fabrication and the need for accommodation in wall detailing, as would be for example, in the case of using couplers, as that we locally increase the diameter of the bar where the couplers are located, or in the case where the bar diameter would be reduced through machining, I will also need some accommodation in the wall detailing. So all of these will not be needed in the case of heat treatment, as the geometry of the bar will remain the same. So how did we do this? So we developed a heat treatment protocol at UC San Diego, and that actually was defined in order to perform the desired properties of in the heat treatment section, which is specifically to reduce the strength of the bar below the yield strength of the original bar, to make sure that the energy dissipation will be concentrated at the desired location, and also increase the elongation capacity of the bar. So we perform a set of tests on this method by locally wrapping the bars with a heating pad and insulation to ensure control heating and cooling. So this is the outcome of heat treatment. So you see that an example bar where the untreated section uses the original color of the bar, and then there is a different color on the heat treated segment, which is actually also make it easier for for labor workers to kind of locate where the heat treated segment is, and therefore they can place it within the wall at the desired location. And then here you see experimental results of engineering stress versus engineering strain of the heat treated and untreated section. So you see that the protocol that we developed is effective uh, in the sense to meet the requirements that we set for the bar. We also conducted a parametric experimental study of the cooling rate tolerances, specifically because we wanted to see what type of quality control do we need to consider when this method is implemented in practice. So therefore, what we did is that we varied the cooling rate from 0.33 to 5, which is a significant variation. And what we noticed is that, in fact, the tensile strength in all cases remained below the expected yield strength of a 706 grade 80 bars, which is the bar type on which we performed this heat treatment. So you see that in all cases, the tensile strength remained below this target limit. And also, what we noticed is that the ordinal magnitude change in the cooling rate produced only a 26% increase the yield strength and a 14% increase in the tensile strength. What that means is that our procedure is relatively versatile and can be applied in practice without any strict quality control of the cooling rates, which may be expected in many cases in practice. So this procedure provides a relatively reliable results, even if there is low quality control in the shop. So what we did next after this experimental analysis, then we move forward with some numerical analysis of how that would look into the designing a prototype hybrid wall with heat treated bars. So therefore, we consider a prototype building, and based on this building, we designed a prototype hybrid wall that incorporates this detail. Here are some numerical results of this wall that uses heat treatment bars. So you see that here the response is relatively stable. Also, the wall experiences pretty good recentering. The residual drifts are below 0.4%. So there is the recentering capability of the wall is pretty good, and also the hysteretic damping that we achieve through the heat treatment meets the requirement of ACI 550.6 that requires a relative energy dissipation of 12.5%. So this is the horizontal black line that is shown here, and the red dots are the relative energy dissipation that were achieved by this wall, and it's essentially corresponding to the energy that is included within the loops shown in the lateral force versus lateral drift graph. And we also plotted what is the equivalent viscous damping for the system. So we also compared we also plotted the PT tendon strain. You see here that the wall also was designed to ensure that for the 2% drift level, which is a target design drift for this type of walls, we also making sure that the strand is not yielding and that is able to preserve its initial strain value, so which is achieved in this case. And then lastly, we also plotted the heat-treated bar strain versus the lateral drift. So in general, based on our experience from the coupon test, we noticed that if the heat-treated bar strain remains below 0.1 1 or 10%, then we should be able to avoid strain localization and necking, which is essentially achieved in this case as the bar strain remained below 0.08. So overall, this work has proposed a new hybrid rocking wall system with the goal to improve the post-earthquake repair of the debonding energy dissipating bars. And how was it done? It was done by strategically concentrating hysteretic action in replaceable bar segments through the use of local heat treatment procedure. So we developed a procedure. In this case, we showed that the procedure is versatile, economical, and effectively implemented in practice. And future work will evaluate the proposed wall system experimentally. Thank you very much.